this unit that you guys are working on is what is called linear systems. Okay, now what the heck is a linear system? Okay, well let me give you some analogies here and some stories here to sort of tell you what this is about. Let's use this right here. Okay, here's a little map of Canada. Now, suppose you are, of course, well, you're of course here in Winnipeg, so we are over here, and you want to get to Edmonton. Okay, now there's different ways that you could go to Edmonton. Now, one way that you could go to Edmonton is you could just drive to Edmonton. So you could just drive to Edmonton, and of course there's a highway, and you could just sort of drive through Regina, something like this. You could drive to straight to Edmonton. Now, of course, this is going to take a while to go there, so it's going to take longer. You might have to spend the night somewhere. You have to spend money on food. There's lots of different things. But that's one option. Another option you could have is maybe you could just fly to Edmonton. So, you take a flight, take a plane, and go right there. Now, of course, this is going to be more expensive probably than just driving a car, or maybe not. You're not spending money on hotel. You're not necessarily spending money for meals as you travel, that type of stuff. You're not spending money on gas really to be flying. Or maybe what you could do is maybe you could do a third option. Maybe you could drive and fly. Maybe there's a really, really cheap flight to Calgary, and then you could rent a car and then drive to Edmonton. So maybe you could do both. Okay, well, these are all different options that people who travel look at all the time, or especially in shipping and receiving and that type of stuff where you're shipping goods from one place to another. What's the best way, cheapest, most efficient way to get something from one place to another place? Well, this is where linear systems could kick in. You could have a formula to calculate and estimate how much each one of these would cost, whether it's driving, the flying, or that, and you sort of look at the formulas and you can sort of put them together and see which one is going to give you the best cost effectiveness based on what you want to do. Okay, here's another one that we could look at. Suppose you are going to get a job and you get a job offer. And in the job offer, there's a couple different jobs maybe that you are looking at and considering for being hired. Now, maybe one of them is going to give you a $5,000 signing bonus if you take their contract. And when you get paid $2,400 a month. Okay, so there you go. There's one. The other job that you are being offered is going to give you a $20,000 signing bonus, and they are going to pay you $1,800 a month. So which one should you pick? Well, people might jump to the 20 grand bonus one because the bonus is way bigger, but you're also getting paid less per month. It depends on how long you plan to work there. If you are going to be working there a long period of time, it would make sense to take the first option. Sure, you have a lower bonus, but at $600 more a month, after a number of years, you'll be making more money with the first option than the other option. If it's just like a short-term thing, like you're only going to be there like a year or something like that, well, then this option would make more sense. So this is where linear systems, again, could kick in, is find out which job would make the most sense depending on how long you are going to stay. So this is another application for it. Okay, let's give you another one. Suppose you're going to build something, okay, and you don't know if maybe you're going to build a bridge or something like that, and you don't know should you use steel or should you use wood in order to actually make it. Well, if you use the steel, this is going to be more expensive to buy steel. Wood is, on the other hand, it's weaker. So do you buy the more expensive steel, which you need less of? Or do you buy the wood, which is cheaper, but you need more of it? Like, which one are you going to pick? So a lot of this has to do with cost effectiveness. If you can get away with, one or the other, that's what you got to figure out. And this is what construction companies and building companies, they do this type of calculation all the time, is which one are we going to pick? Steel's more expensive, but we need less. Wood is cheaper, but we need more. Well, which one is going to work best for the situation? Do we need tons and tons and tons of wood or just a little bit of steel? Like, these are all decisions that people make all the time. And this, again, where linear systems kick in, where you have a formula or expression, you have another formula and expression. You see how the two relate to each other, see how one changes compared to the other one, where's the common bonds that they have, that type of stuff. Okay, so for example, if we went back to that job one for a second, and we'll sort of lay things out in terms of how we might actually do something like this. If we do the first one here, if we looked at this one right here, and we sort of did a little graph here, because obviously it has a lot to do with graph and stuff like that. And we look at money and time. If we look at that first one there, the money you start with is only $5,000. Okay, and then you get paid $2,400 a month. So it might look something like this. As the time goes on, you make more and more and more money. Where on the other one, if we look at the second option, this one you started at $20,000, but the graph won't go up as quickly. It's going to go up slower because you're only making $1,800 a month. Well, right there where those two graphs intersect, that's the critical point that you want to meet. You want to know where that is. How long would you have to stay to make one better than the other? And this is where linear systems kick in. Whether you do this with the distance graph going across Canada, driving and flying, whether you do steel versus wood, this is the type of thing businesses and companies and people do all the time. You got algorithms and formulas for cost effectiveness and transporting stuff and doing its encoding and computer programs and so many things use the basic idea of systems with equations. These are we're just linear systems, but it expands to way more than just linear systems. The idea of taking two functions, two formulas, three formulas, sometimes 4, 5, 6 formulas, and having them come together and which one works better when, that type of stuff. That is what linear systems is all about. Okay, so this is the type of thing that we are going to be looking at and starting you guys off with. Okay, so let's take this stuff right here. We're just going to get rid of it. Okay, we'll delete that and get going with a couple other ideas here. Okay, so linear systems. What are linear systems about? Okay, well, this is when you actually have multiple, you can call them formulas, you can call them functions, you can call them whatever you want. When you have multiple formulas and functions, that should be an S, when you have multiple formulas and functions, and you look at how do they relate to each other? Do they have a common bond? Okay, when is one going to be better than the other? Okay, that type of thing. So we could even go back to what we had before when we looked at that little money graph with the jobs and stuff like that. We had something like this. We had one that started here that got really, really high. Then we had one here that went something like this. Right there, there's your critical point right there. Okay, right where the two intersect. So is there some kind of a critical intersection? Okay, is there a critical intersection that we have to look at? Is one of them better before or afterwards? These are all just different things that we kick into. Okay, so is there a critical intersection? Do they have a common point? Is one better before or after? This is where linear systems kick in. And there's different ways we can actually do this and figure this out, but there's the types of things that we can actually do. We'll also try and do things like, try and combine expressions together. Okay, we can try and combine expressions, which allows us to actually make new connections between different types of variables and stuff like that. So there's lots of different things we can actually do, and there's lots of things this actually leads into in math and science and business and a whole bunch of other stuff. Okay, so there's some basic ideas that we kick around with and fool around with a little bit, but one of the basic things is to look at, there are basically three possible outcomes when you actually start putting systems together. So there's three possible outcomes. The first one is what is called an independent. Okay, actually this right there is what is called an independent outcome. Okay, so if you have an independent outcome, that means there is one solution. They'll intersect one time. The two formulas are, or the two expressions, the two functions, the two formulas, they're independent of each other. They can do their own thing, and they'll end up only having one solution. They only crisscross in one place. And that's what's called an independent solution. The second one is what is called a dependent solution. Okay, there's what's called a dependent solution. And dependent solutions have infinite solutions. Okay, so these guys are always matched up all the time. Okay, so the first graph we had up here, that is an independent solution when they crisscross just one place. So this would be independent. A dependent solution is kind of weird because if you graphed a dependent solution, you graph one line, maybe something like this, and then when you graph the other line, it is literally right on top of it. So they're always matched up. They have infinite solutions all the time. And the third option is what's called an inconsistent solution. And there are no solutions whatsoever for an inconsistent system. Okay, so they have absolutely no solutions whatsoever. So you graph that out. Those, you graph one, it might look like this, and the other one would look like this. They are actually parallel to each other. So these two lines are going to be actually create parallel lines. That's one of the reasons you guys looked at parallel slopes in your linear functions type stuff. So these are the basic ideas behind linear systems. I gave you some scenarios and that kind of stuff. And it's when you have multiple functions, multiple formulas, multiple things going on. You want to see how they connect to each other. Do they have something in common? Do they not have something in common? Is there a place where they actually intersect? Is one system going to, or one expression going to work better before or after this intersection? We sometimes will tie things together and do things like that. And then we have our outcomes. We have the independent ones where they only have one possible solution. We've got dependent outcomes where they have infinite solutions where they're always going to be the same. They're always going to connect to each other. And then we've got the inconsistent ones where one really has absolutely nothing to do with the other one, which does actually happen. And again, that's where your parallel slope type ideas kick in from the previous linear functions unit. Okay, so these are some of the ideas behind linear systems and what we're going to be working with.